Today I'm going to go over our density lecture for Principles of Chemistry Lab. First of all, I'm going to go over what chemistry is. Chemistry is the study of matter. We define matter as anything that has mass and it takes up space. So, for example, a cup of water is matter. It's taking up space and it has mass. Or your body on planet Earth is matter. In chemistry, we have two changes that take place. We have a chemical change and a physical change. So let me go over what a chemical change is. Chemical change is pretty much a chemical reaction. And we can define that as some substances are being used up and other substances are being formed. On the other hand, physical change is change of state. So if you go from a solid to liquid, or liquid back to solid, or liquid to gas, gas to liquid, these are change of states. If you have water melting, water boiling, then we get gas. Water freezing, we get ice. Another example here I can give is if substances dissolve, like placing sugar in coffee. The sugar dissolves into the coffee, and that's a physical change. In science, we have a thing called scientific method, which is testing of theories. You'll have a fact, a proven fact, that you can obtain a hypothesis on, and then you test the hypothesis by doing experiments, and then you get your results, and you can form theories. I'm going to go over numbers now. In science, we use exponential notations, which is based on the powers of 10. So it's either 10 to power something. For example, we have here 2.95 times 10 to the 6. So how do we write that? 10 to the 6, so we move the decimal. If it's positive, we move it to the right. Positive, right, negative, left. So if it's positive, we move it to the right. 2.95, we move it 6 times to the right. So that's 1, 2, 3, 4, 5, 6. Then we have 1, 2, 3, 4 zeros. That would be 295 and 4 zeros. And then if we have negative 6, so we move the decimal point to the left 6 times. 1, 2, 3, 4, 5, 6. Now we have 1, 2, 3, 4, 5 zeros. So we have 0.345 zeros, then 295. And you can go vice versa. In chemistry, we use significant figures. So it's very important for you to understand significant figures. We have a couple of rules. I'm going to go over each rule. I think it's 6 or 7 rules. So rule number 1, non-zero digits are always significant. So anything that's not a zero is significant. For example, we have 233.1. So we have 1, 2, 3, 4 non-zeros here. That will be 4 significant figure. Here we have 2.3 grams. That's 2 non-zeros, 2 significant figure. Our second rule says that zeros at the beginning of a number are never significant. So that means we have here 0.0055. All these zeros are not significant. So how many significant figures do we have here? 2. It's the 2 non-zeros right here. Next example, we have 0.3456 grams. This 0 is beginning of a number, therefore it's never significant. Now we have 1, 2, 3, 4 significance. Rule number 3 states that zeros between non-zero digits are always significant. So if you have a 0 between 2 non-zero numbers, then it'll count as a significant figure. Here we have an example that says 2.045. So these 2, 0, 4, 5. That's 4 significant figures. Now here, our next example, we have 8.0506. You see here we have 2 zeros, but they're all between 2 digits of non-zeros. Therefore, we have 5 significant figures. Our next rule states that zeros at the end of a number that contains a decimal point are always significant. So, if you have a decimal point and you have zeros following the decimal point, those count. Here we have 3.00. 3.00, that's 3 significant figures. Now here is a combination. We have 0.0450. So after the decimal point, the 0 after a non-zero digit will count. This will count. But before a non-zero digit, this one, will not count. So how many significant figures are these? We have 1, 2, 3. 3 significant figures. Rule number 5. Zeros at the end of a number that contains no decimal point may or may not be significant. So here we have example 2,500 grams. This will be these 2 zeros are not significant, therefore you have 2 sig figs. On the other hand, 2.50, since this 0 is following the decimal point, it'll count. So this will be 3 sig figs. So if we add another 0 to the end, 2.500, both of these zeros count. Therefore we have 4 significant figures. Rule number 6, adding or subtracting sig figs. So when you're adding or subtracting, you use the least decimal point. And when multiplying and dividing, you use the least significant figure. So let me go over a problem here. Problem 1. Multiply with correct significant figures. We have 7.9 times 10 to the power of 8 times 6.77 times 10 to the power of minus 5. So which one is the correct answer here? I did the math for you in advance, but we have to figure out the correct significant figures. We have here 7.9 and 6.77. Because we're multiplying, we will take, what does the rule state here? Use the least significant figures. That means the least significant figure is 7.9. So the correct answer here would be 5.3 times 10 to the power of 4th. Not 5.344. This will be 3 significant figures. Problem 2, it says divide using correct significant figures. Again, we're working on sig figs here, so I already worked it out for you. We have 9.08 times 10 to the 16th divided by 5.6 times 10 to the 6th. We have to use as you can see here, multiply and divide are the same rule. We have to use the least number of significant figures. This one is 1, 2, 3, 3 sig figs. And here we have 2 sig figs. So what's the answer? The top one or the bottom one? The answer is 1.6 times 10 to the power of 10. 2 sig figs. Alright, I'm going to go over measurement now. Measurement consists of 2 parts. What are these parts? Part number 1 is a number, and part number 2 is unit. A number by itself is not enough. The unit must also be stated. So let me write that. Number by itself is not enough. The unit must also be stated. Example, 5 grams. If you just say 5 in chemistry, I have no idea what you're talking about. So we have 2 different systems. We have the English system, which consists of pounds, miles, yard. These are all the English system. And then we have the metric system, which goes by okay, this is a weird way I remember this. Is King Henry died but didn't call mom. I don't know. I just learned it in 8th grade science class. So B is the base. Let's say we're using grams, right? If we want our grams in kilograms, which is here, the kilograms, we'll move our digit to the left 3 times, and then if we want milligrams, we'll move it to the right 3 times. So the metric system works by the power of 10. Power of 10. So we only we'll have the same numbers, but we'll only be moving with powers of 10s. Let me go over the base units in the metric system. For length, we use meters. For volume, we use liters. For mass, we use grams. Time, we use second. Temperature, we use Kelvin, which is a capital K. Energy, we use joules. And amount of substance in chemistry, we use mole. Let me go over length. So the base unit of length is meters. To convert one metric unit to another, we only have to move the decimal point. Okay. So we have the King Henry died but didn't call mom. I know it's funny, but it's the only way I can remember. So these are powers of 10s. So we have 1 here, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3. Here we have 10 to the negative power of 1, 10 to the negative power of 2, 10 to the negative power of 3. This here is micro, which is 10 to the power of minus 6. Nano is 10 to the power of minus 9. Put these dotted lines here because these go by 3's. And then on this side, after kilo, we have mega, which is 10 to the power of 6, and giga is 10 to the power of 9. So let me write here, we have giga, mega, kilo, hecto, deca. And then this is your base. Could be grams, liters. And then we have deci, centi, milli, micro, and nano. So let's do an example. 1 kilometer is equal to how many meters? So we have a kilometer here. Let me use a different color. We have a kilometer here, and we're going to go to the base of meters. So we use 1 kilometer is 1, 2, 3. We add 3 zeros, so it's 1, 2, 3. Because technically this is 1.0 here. We move the decimal point. We add the 3 zeros, so that's 1,000 meters. Then we have 1 centimeter. 1 centimeter is here. We have to go to meters, so we go back to the base. Centimeter, we move back 1, 2. So we'll take the 1.0 decimal point and we'll move back 2. 1, 2. That would be 0.01 meters. And then we have our last example. Let me pick a different color here. 1 nanometer, and we have to get to meters. So we have 1 nanometer, which is right here, and we have to go to the base meter, which is right here. So we have, remember nano is minus 9, so when you go from here to here, we're actually moving 3, and then from micro to milli, we're moving another 3, and then it's 1, 1, 2, and 3. So that's 9 total. So 1 nanometer is actually 10 to the minus 9 meters. Next we have volume. Volume is space that a substance can occupy. A substance can be anything, liquid, solid, gas. The base unit of volume is liters. Some conversion, we have 1 milliliter is equal to 10 to the minus 3 liters, or if we have a decimal point here, we go back 3 times, 1, 2, 3. That would be 0.001 liter. And here 10 to the third liter is equal, sorry, this is supposed to say milliliter, is equal to 1 liter. So our decimal point is here. We move it 3 times, 1, 2, 3. There we'll have 1,000. 1,000 milliliters is equal to 1 liter. Side note, 1 milliliter is exactly equal to 1 cubic centimeters. Cubic centimeters is centimeters cubed to the third power. It's also noted as cc. So 1 milliliter is equal to 1 cubic centimeter. If we convert our milliliters to liters, then it's 1,000 times. So 1 liter is 1,000 cubic centimeters. Let me go over mass now. Mass is the quantity of a matter in an object. The base unit of mass is grams. So 1 kilogram, same as liters here. 1 kilogram is 1,000 grams. 1 milligram is 10 to the minus third, so 0.001 gram. What do we use to measure mass? We use a balance. It's not scale, it's called a balance. Let me explain to you the difference between mass and weight. Mass is independent of location. Weight is not independent of location. Weight is the force a mass experiences under the pull of gravity. So weight is defined by gravity. Your weight on Earth versus Moon. You will weigh heavier on Earth because the gravity on Earth is higher. It'll pull you down stronger than the gravity on the Moon. But this doesn't mean your body size is changing. Your mass is still the same. Your body size is the same. You're still the same person, even if you're on Earth or on the Moon. But your weight will be different. For nurses, drug doses are prescribed on the basis of body mass. So let's say you're giving the same drug to your patient on the Moon. Doesn't mean that the dosage should be less. The dosage will be given depending on the patient's body mass. Time. Units of time are all the same in all the systems. The base unit of time is second. We know that 60 seconds is 1 minute, 60 minutes is 1 hour. You'll need to know this, I'm sure you already do, for any conversions we do. Temperature. There are 3 different temperatures. We have Fahrenheit, Celsius, and Kelvin. To convert Fahrenheit to Celsius, we use this equation here. Degrees Fahrenheit is equal to 9/5 times whatever degrees Celsius you have plus 32. So you will multiply first and then you add. But here, if you're converting from Celsius to Fahrenheit, you will take your Fahrenheit temperature minus the 32, whatever number you get, and then you multiply with 5/9. Kelvin is given by 273.15 plus the degrees in Celsius. So we can't use Kelvin with Fahrenheit. If you have a Fahrenheit and you're trying to get to Kelvin, you gotta convert Fahrenheit to Celsius and then the Celsius to Kelvin. Degrees Celsius is also whatever Kelvin temperature you have minus 273.15 will give you Celsius. 0 degrees Celsius is equal to 32 degrees Fahrenheit. That's the freezing point of water, where water becomes ice. And then we have absolute zero. Absolute zero is 0 Kelvin. Not okay, that's 0 and then capital K for Kelvin, which is the lowest possible temperature, which is negative 273.15 degrees Celsius. At this temperature, all molecules stop moving altogether. That means everything stops at that point. If you can get to 0 Kelvin, then you can technically stop time. Let me go over problem 3 here. Problem 3 says convert body temperature 98.6 degrees Fahrenheit to Celsius. So what's the equation we're going to use? We're going to go from Fahrenheit to Celsius. So we have to find C. We have to calculate Celsius. The equation will be degrees Celsius is equal to 5/9 times our 98.6 degrees Fahrenheit minus 32, and we'll get it in degrees Celsius. So if you do the calculation, this will come out to 37.0 degrees Celsius. Why did I write 37.0? Because we had 3 sig figs here. 98.6 is 3 sig fig. To convert from one unit to another, we use the factor label method. Here, the equations are set up so that all unwanted units cancel, and whatever unit you want to end up with will remain there. So we have an important point here. When multiplying numbers, we also multiply units, and when dividing numbers, we also divide units. You have to keep track of your units, or else your math will not be correct. Things will get more dense in the future, and if you don't keep up with your units, you will not know what you're calculating. I'll show you guys an example later on. And then another important point here, we use conversion factors when converting from one unit to another. So let me go over problem 4 here. It says convert 568 grams to pounds and correct significant figures. So these are the conversion factors. We have 2 here, conversion factors. So it says 1 pound is equal to 453.6 grams. Likewise, 453.6 grams is equal to 1 pound. So how do we convert grams to pounds? Let me show you how important it is to keep your units. We have 568 grams, right? So which conversion do we use? Let's check. Let's use the first one. It says 1 pound per 453.6 grams. So if we keep our units, now we see here it says pounds over grams. We have grams here. Let me write a different color. So our grams cancel out because we know gram over gram is equal to 1. Anything over the same unit is equal to 1. And we end up with what? If we do the math, we have 1.25 pounds. So why did I write 1.25? We have 568 grams. That's 3 significant figures. Over here, 453.6, this is 4 significant figures. But because we're multiplying, we take the least significant figures. That's why it's 1.25 pounds. 3 significant figures. So let's say we used, this conversion. Let's see how that's going to work out. This is why it's important to keep your units when you're calculating. We have 568 grams times 453.6 grams per 1 pound. Now, you see how we can't cancel out grams, we can't get rid of pounds, so what do we end up with? If we do the math here, we have 568 times 453.6, which is 257,644.8. Okay, now we have our grams times grams, which is grams squared over pounds. If we write this in the correct significant figure, we have 1 2, 3 here. 1, 2, 3, 4. We're multiplying, so it's going to be 3 significant figures. That would be written in scientific notation. So it's 2.57. Actually rounding it up, 2.58 times 1, 2, 3, 4, 5, 10 to the power of 5 gram squared per pound. Now our question here says convert 568 grams to pounds. So our answer needs to be in pounds. This answer is not in pounds, it's grams squared per pound. Therefore, if you keep your units, you'll know that you're using the wrong conversion. This is not correct. This is the correct answer. Now I'm gonna go over problem 6. Now we have multiple conversions. Here's why another reason you need to keep your units. It says convert 55 miles per hour to meters per second. So we have 55 miles per 1 hour. And we have to get to meters per second. So how many kilometers are in a mile? If you look up online, you can get the conversion that 1.609 kilometers are in 1 mile. Right? So now here we see that the mile and mile cancel out. Now we're left with kilometers per hour. What's our next conversion factor? So we have to go from kilometers to meters. We know that 1,000 meters are in 1 kilometer. Now we see again our kilometers cancel out. We're left with meters per hour, and we have to get to meters per second. So we have to convert hour to second. The first thing we do, we convert hour to seconds, hours to minutes. So we have 1 hour. In 1 hour we have 60 minutes. Now our hours are canceled out. What are we left with? Meters per minute. And we have to go to seconds. So our next and final conversion, we have 1 minute per 60 seconds. And finally, our minutes are canceled out. And what are we left with? Meters per second. So we have 55 times 1.609 times 1,000 divided by 60 times 60. And on the top we have meters, and on the bottom we have seconds. So this will give you actually, let me tell you exactly what it gives you. This will equal to 24.5819 meters per second. So let's look at our significant figures now. What do we have here? We have 2 significant figures. Therefore, our answer needs to be in 2 significant figures. Therefore, it's about 25 meters per second. Now let me go over states of matter. Matter exists in 3 states. What are these states? We have gas, liquid, solid. So it says no definite shape or volume. Gas has no definite shape or volume. It can fill any container and it can be compressed. So gas can be compressed. 2. We have no definite shape but definite volume. What's that? Liquid. Liquid has no shape but it has a volume. Liquids are slightly compressible. And finally, we have a definite shape and volume. That's solid. Solids are incompressible. You cannot compress any solid. Whether a substance is a gas, liquid, or solid depends on its temperature and pressure. How do I explain this to you? So, at sea level, water boils at 100 degrees. And then we have a specific pressure here. So let's say we have a specific pressure. But let's say you're on top of Mount Everest. Water boils at around 70 degrees. Why is that? Because the pressure is different. Another important point, chemical identity of a substance doesn't change when it is converted from one state to another. So water is still water even if it's ice or boiling water turns into steam, or your liquid water, it's still water. You still have H2O. 2 hydrogens per oxygen. The last thing I'm going to go over is density and specific gravity. You need to know this density for your Cengage assignment and your Beyond Labs experiment. So density is defined as the degree of consistency measured by the quantity of mass per unit volume. So it's mass per unit volume. We have an example here. When oil and water mix, we see that they will eventually separate. If you put oil in a cup of water, you'll have a separation. Why is this separation? This separation is due to the densities being different. We know that oil is not soluble in water. Why is that? Oil is not soluble in water because water has a higher density than oil. So, as stated here, substances that have lower densities will float on top. So you'll have oil on top, water on the bottom. Density is calculated by dividing the mass of a substance by its volume. So this is your equation for density that you will need for this week's work. Density is equal to mass over volume. Let me go over a problem here. What is the density in grams per milliliter if 98.6 milliliter of a liquid has a mass of 46.8 grams? So, what is the density? So we need D. D D is equal to mass over volume. So what's mass? Liquid has a mass of 46.8 grams over, what's the volume? This is the volume here. 98.6 milliliters. That is calculated to density is equal to 0.475 grams per milliliter. And we have three significant figures divided by three significant figures is equal to three significant figures. 1, 2, 3. Another problem I'm going to go over here, problem 8, says, what is the volume in milliliters of a small irregularly shaped iron that has a mass of 373 grams? So we have to find the volume in milliliters. So volume in milliliters. Small irregularly shaped iron. We have an iron that has a mass of 373. So mass is equal to 373 grams. Iron. We know it's iron, so we have to look up density of iron. And I already looked that up, which is 7.87 grams per centimeter cubed. So we need our volume in milliliters, but our density is in centimeters cubed. Do you guys remember the conversion I told you before? 1 milliliter is equal to 1 centimeter cubed, which is equal to 1 cubic centimeter. So let's do the math now. I'm gonna use a different color. So density is equal to mass over volume. We need volume. We have to get volume alone. So how do we do that? Let's get rid of density first. We divide it by D. I write it this way. Times 1 over D times 1 over D. The D's get cancelled out, so we have 1 is equal to M over V times 1 over D. Now we have to get our V alone. How do we get V alone? So we're going to multiply by V on both sides. The V's cancel out here, and we're left with V is equal to mass over density. What was our mass? Our mass is 373 grams. Density is 7.87 grams per centimeter cubed. That is equal to, I already calculated this for you guys, 47.4 grams get cancelled out. Centimeter cubed moves to the top. Centimeter cubed, which is equal to 47.4 milliliters. That's our answer. Now let me go over specific gravity. Specific gravity is numerically the same as density, but it has no units, so it's dimensionless. because it is defined as a comparison of the density of a substance with the density of water, which is taken as a standard. So here's an example for you to understand better. The density of copper at 20 degrees Celsius is 8.92 grams per milliliters. And then the density of water at 20 degrees Celsius is 1.00 grams per milliliter. Hence, copper is 8.92 times as dense as water, because this is 1. So therefore, the specific gravity, which is specific gravity, at 20 degrees Celsius is 8.92 with no units, because the units cancel out. So if you do 8.92 grams per milliliter over 1.00 grams per milliliter, these cancel out and you're left with 8.92. The specific gravity of any substance is always numerically equal to its density. Okay, so it's always going to equal to the density, just with no units. That is only possible if the density is in grams per milliliter or grams per cubic centimeter. We measure specific gravity using a hydrometer. A hydrometer consists of a weighted glass bulb, which is here. That's a glass bulb that is inserted into a liquid and allowed to float. The stem of the hydrometer has a calibration mark, which are the marks here. And specific gravity is read where the meniscus hits the marking. So this image here is zoomed in of this section. So when you have any liquid, to read the meniscus, you'll have this U shape. To read the meniscus, we have to read it from the lowest point, right here. We don't take the average of this. We don't read the top number. We read where the curve is on the least point. That's how you read the meniscus. So, in clinical laboratories, hydrometers are used to measure the density of urine samples. So, this is known as a urinometer. It's pretty much a hydrometer, but just for urine samples. So what is this used for? If you use this urinometer for a normal urine sample, your meniscus reading, remember the meniscus reading, should be anywhere from 1.010 to 1.030. This is a normal reading. Let's say you have a diabetic patient. This meniscus reading would be abnormally high. Or let's say if you have a kidney disease patient, their meniscus reading of their urine sample would be abnormally low. So keep in mind, this is a normal range for the nurses out there. Let me go over our last problem here for today. Problem 9. What is the specific gravity if the density of ethanol at 20 degrees Celsius is 0.789 grams per milliliter? So, specific gravity is equal to, we have here 0.789 grams per milliliter divided by the water. If you guys remember, it was 1.00 grams per milliliter. This is at 20 degrees Celsius. At different temperatures, these values will be different. So our specific gravity for ethanol will be 0.789. And that's the answer. Okay guys, that's it for today. If you have any questions, please do email me.